technologies to generate electricity. So you have, for example, solar, wind, or hydro. In Brazil and Northern Europe, hydraulic generation is one of the main sources of energy. This technology has one of the following important characteristics. So first, it's a renewable energy. Second, the low cost of energy generation if compared to other sources. So we have an important initial investment to build the structure, but after it's low cost. Third, it allows the system to store energy in the form of water in the reservoir. So for other sources, we probably need a stockage device, which is not the case in the case of hydro energy. And fourth, the difficulty in predicting the amount of rain and snow at any time scale makes the water inflows uncertain. So the price signal represents the opportunity cost. That is, we consider the possibility of shortage of energy and the cost of other supply sources in future periods. So for example, if it rains less than expected, you need to activate other power plants. And these other power plants can be more expensive. This extra cost is an important component of the price signal. Second, the randomness that comes from diverse inflow scenarios make us consider different possibilities of future cost function. We consider possibilities of a larger or smaller amount of rain and snow and the consequences for the system. So in this context, we will talk about two difficulties. So difficulty one, often the set of Lagrange multipliers pi is not a singleton. So it's necessary to define a selection that gives always the same price among all possibilities in the set. One example of this selection could be the minimal norm price. And the difficulty two, taking uncertainty into account means that the price will be a random vector. So here we have pi of xi1 to xis, where xis are the scenarios. The distribution of the price signal depends on the scenarios you consider and the probability p in the scenario set. So to illustrate this difficulty too, we show a simulation we have done in a two-stage model with 80 scenarios. Here we consider two samples, xi1 and xi2. And we see the different distributions of price signal of these two samples. These two distributions have different expected values of variance, and these parameters are important to make decisions. So we ask if a regularization can help us to smooth this distribution. So about the mathematical model to the two-stage problem with energy generation. So in long-term problems, decisions need to be coupled in time. So for example, for the energy generation problem, the link between time t and t plus 1 is the water balance equation. So here we present a simple formulation of two-stage problem for the energy generation, and we consider xi, the generation of the ith unit. We aim to minimize costs in stages 1 and 2. All variables are non-negative. We have some equations that here are summarized by bxi less or equal bi. For example, the demand equation or some box equations as the capacity. And we have the water balance equation, tx1 plus wx2 equals inflow xi, where xi represents the randomness in the problem that are in inflows. This equation physically means that we cannot lose water in the system. The level of the reservoir at time t plus 1 is the same as time t minus what we use to generate electricity and eventually the spillage. Associated to each water balance equation and each psi, we have a Lagrange multiplier pi by xi. So this Lagrange multiplier pi bar psi is associated to the second stage problem. We can break this problem in two, and in the second stage problem depends on the random variable xi. So for xi, we have this different water balance equation. And also the second stage problem depends on the decision we take in the first stage problem. The first stage problem minimizes the cost in the first stage and consider the expected value of the future cost function, considering all possibilities of psi in the random set. The second stage is also known as the future cost function. So the future cost function is an optimization problem and has a dual. When we compute the dual, we find the Lagrange multipliers. Pi here is the Lagrange multiplier for the water balance equation, and pi b the Lagrange multiplier for other equations. So we consider, what we propose is regularize this dual future cost function. It means that in the objective function, we add a term that is pi squared multiplied by a parameter beta over 2. This new future cost function is called beta q beta, and it is the dual regularized future cost function. When we compute the dual of this new optimization problem, we turn to another formulation. With this new formulation, the water balance equation is incorporated in the objective function. So the choice of beta is important to control how much we want to relax this constraint. So the water balance equation was in the feasible set, now it is in the objective function. And we don't want to forget this equation, we just want to relax it. When we consider the randomness in the problem, we have a set omega of psi1 to psi-s with probabilities p1 to ps, and we consider the possibilities of future cost function multiplied by the respective probability by ps. Also, the second stage variable x2 depends on the scenario s. So now I will present the theoretical results that are present in the manuscript, and they talk about the asymptotic behavior of beta when it's close to 0. So the results I will present here are in an article published in the Journal of Optimization Theory and Application, and it's called Multiplier Stabilization Applied to Two-Stage Stochastic Programs. It is a collaboration with Claudia Sagastizábal and Mikhail Solodov. So we remind the one-level formulation for one psi. It is a linear programming program, and the regularized one-level formulation that is a quadratic programming program because of this quadratic term in the objective function. So to give a nonlinear perspective of the problem, we consider the abstract quadratic program. So here we aim to minimize f of x, where f has a linear part, there is a scalar product of g and x, and a nonlinear part, there is a scalar product of x and hx, for x in x and ax minus b equals 0. Here x is the non-negative axis and b is in the image of a. Also, we define x beta, the solution of the penalized problem, minimum of f of x plus 1 over 2 beta ax minus b squared. So here we have the same formulation of the regularized, one-level regularized formulation. We call this problem pi beta and the original problem p beta and the original problem p. So given a sequence beta k, we consider the sequence where we replace beta for beta k, and we call it big F k of x. So first we present results that are standard in this context. So we talk about the standard exterior penalty methods. So this result states that if you have a decreasing sequence beta and xk, a solution of the problem p beta k, the sequence will have the following behavior. Big fk xk will be an increasing sequence. The penalization sequence axk minus b will be a decreasing sequence, and fxk will be an increasing sequence. In addition, if beta k is going to 0, the optimal value and the optimal value of the problem p is finite. Every accumulation point of the sequence xk, if it exists, is a global solution of p. So what is important to note here is that we assume that the existence of an accumulation point. So if this accumulation point does not exist, or if the sequence is not bounded, the result can be vacuous. Another result in the same context is the dual convergence of quadratic penalty method. In this result, we assume that x equal Rn, and we consider x bar an accumulation point of xk, where xk is the solution for p beta k. So we also assume the linear independence constraint qualification at x bar, what in our case means that A is full rank. So x bar is a stationary point of p, and the subsequence pi kj, here defined as a xk minus b over beta k, converts to the unique Lagrange multiplier pi bar associated to x bar. In this result, we also assume that implicitly that the sequence is bounded, since we don't show that there is an accumulation point. Another thing to note is that the linear independence constraint is not true for many applied problems. So now we state the theorem as we proved in the manuscript. This theorem will assume conditions 1 or 2. I will talk about these conditions in the next slide, and now I will focus in the result. So if the condition 1 is true for problem P, or condition 2 is true at x bar, and h is positive semi-definite, we have that for any sequence of parameters beta k, not necessarily monotone, and any sequence xk generated by the penalty scheme, any sequence is bounded, which is different that we have seen before. Also, if beta k is decreasing, all accumulation points of xk are solutions of P. In particular, in the second case above, the whole sequence converges to the unique solution x bar. So we see that this result is different from other ones because we prove that the sequence is bounded. So we are not assuming an accumulation point, we are proving that it exists. So now about the conditions 1 and 2, or 1 or 2 that are necessary to our theorem. Condition 1 states that H is positive for D in the kernel of A. And condition 2 states that H is positive restricted to the critical cone in X bar. This critical cone is the intersection of the kernel of A and is decreasing directions with respect to the objective function of our problem, where this direction di is larger than 0 when xi bar is equal 0. This last part of the critical cone comes from the critical cone of the non-negative constraint. We note that in the linear case, condition 2 is equivalent to the uniqueness of the solution x bar. This is because since h is 0 for the linear case, like the energy problem, for condition 2 to be true, we need the critical cone to be 0. If the critical cone is 0, any decision point to the feasible set is not a decreasing direction. So it means that the solution x bar will be unique. On the other hand, we also note that by itself, condition 1 implies condition 2. But we note that you can use condition 1 for a non-convex problem, and you can use condition 2 for a convex problem, since the critical cone is an object for convex sets. So concerning the dual variable, we know that pi k is equal to a xk minus b over beta k. This formula comes from the KKT theorem. We have just proved that a xk minus b are going to 0, since xk are going to a feasible set of the original problem. Beta k is also going to 0. So the questions that arise naturally from this formula is that if pi k is bounded and if pi k converges. To answer these questions, we have another theorem called, also proved in the manuscript, called convergence of the multiplier estimates. And it states that for a decreasing sequence beta k and beta k going to 0, we assume that condition 1 or condition 2 hold, and we take an accumulation point x bar of the sequence xk. This accumulation point exists since you have already seen that for the theorem for the primal convergence that it exists. We also assume a condition 3 that I will explain in the next slide, that it holds x bar. So with these conditions, we have that the sequence mu kj associated, the Lagrange multiplier associated to the non-negative constraint is bounded. If you consider the accumulation point of this sequence, mu bar, and the corresponding subsequence pi kj, we have that this pi kj is convergent to pi hat, the minimal norm solution of the following optimization problem. This optimization problem corresponds to solve the minimal norm Lagrange multiplier over the Lagrange multipliers of the original problem. So it's the minimal norm Lagrange multiplier of the problem P. We conclude that the point x bar, pi hat, mu bar is a primal dual solution of P. So this result gives a selection mechanism for the price. Among the set of multipliers, the procedure will always output the same one. So it's a systematic rule. Now about condition 3. It states that for a feasible x bar, if you write 0 equals at pi plus mu, for mu in the normal cone in x bar, it implies that mu equals 0. We compare this condition to the famous Mangasarian-Fromovitz condition, that for a feasible x bar, if you write 0 equals a transpose pi plus mu when we're in the normal cone, it implies that pi mu equals 0. The Mangasarian-Fromovitz condition is equivalent to the compactness of the set of Lagrange multipliers. Clearly, condition 3 is weaker than the Mangasarian form of its condition and thus is not restrictive. Okay, now I present the illustration of the approach. I represent two examples. First, one example that illustrates this asymptotic behavior of beta that we talk in the theorems. And second, another example that talks about the distribution of the price. So first, we consider this example in R2. It's a simple example that you can solve analytically. We aim to minimize this Cx1 plus Qx2, where these are vectors in R2. And we have this technology matrix of the joint equation. So here we consider two scenarios, psi, psi1, and psi2. What we see is that when we solve the problem for beta equals 0, the answer we have is a norm of like an expected price signal with norm 25.51. When we solve the regularized problem for beta equals 1, 0.5, and 0.1, we approximate another Lagrange multiplier with norm close to 19.4. We see in the drawing that in the graph that the line, the black line represents the sets of Lagrange multipliers. The X in black represents the expected value of the Lagrange multiplier when we solve the original problem. In blue, we have the Lagrange multiplier when we converge when we solve the regularized problem. So, and in pink, we have 0. So we see that it's a minimal norm Lagrange multiplier. So we see here that we have, when you have this set of Lagrange multipliers, we can, by regularization, approximate the minimal norm Lagrange multiplier. Now the other example, it is a well-known example in three-stage in stochastic optimization. And it aims to model the uncertainty in the demand. So when we are not sure that we can fulfill the demand, and if we are not able to do it, we need to buy it in the spot market. So this example is also simple. So we can write the future cost function in this synthetic way. And also we can write analytically the distribution of the price signal. So we see here that the distribution of pi psi is q if x1 is greater than psi, and minus q if x1 is smaller than psi. So if the distribution psi is symmetric, we can compute that the expected value of pi bar is 0, and the variance of pi bar is q squared. When we see the regularized problem for this example, we have the same formulation that we have already seen, where the constraint now is in the objective function multiplied by a parameter 1 over 2 beta. And we can also compute analytically the distribution of the Lagrange multiplier pi beta psi. So we see that here we have three possibilities, and two of them are the same we had before, but we have another possibility that is in between, in a set between these other two sets, where the price is psi minus x1 over 2 beta. We can prove, as shown in the manuscript, that the variance for pi beta is less or equal to the variance of pi. So regularization, in this case, reduces the variance of the price signal. One idea we can have about this new distribution of pi is that we can plot the graphic for xi equals 0 of pi in function of the first stage decisions x1. What you see is that when beta equals 0, we have a pi that is a step function, that a constant by parts. So when we increase the values of beta, there is a linear part that is in between, and that becomes larger when beta is larger. So about the distribution of price, we can also simulate. So we simulate with psi in the distribution, a normal distribution with expected value 0. And Q equals 5, C equals 5, beta equals 1 for 200 scenarios. What you see is that the non-regularized price signal has this binary distribution where we have two possible values that oscillate. And the regularized price signal has this more smooth distribution. So the regularized distribution is preferable for applications because it's more stable with respect to samples. It means that if you consider another sample Xi1, Xi2, the regularized price signal seems to be closer than the non-regularized price signal. And also the expected value is closer to the expected value of the real distribution. For example, in this case, the real distribution has expected value 0, the non-regularized distribution has expected value 0.8, and the regularized distribution has expected value 0.2. So we also can write pi beta because of the KKT equations in terms of the equation we regularize. And what we see is that from the distribution of pi and the value of beta, we can have an idea about we can understand how much we violate this equation. So, for example, here beta equals 1. We know that pi beta is between -5 and 5, and it's around 0. So we know that the violation of the equation will have the same behavior. This choice of beta is the same for the energy problem. We are guided by how much we relax this constraint. So now I'll talk about the application to the generation problem that was developed with ENGIE and is about the North European energy system. So this work was developed in Paris with ENGIE, with supervisors Andreas Hermann and Guillaume Erbs. The results I present here are in an article in final stage of preparation to be submitted to IJOR. It's called Increasing Reliability of Price Signals in Long-Term Energy Management Problems. It is a collaboration with Guillaume Erbs, Claudia Sagastizábal, and Mikhail Solodov. So the Northern European energy generation is composed by hydro, wind, thermal, and solar power plants. So we see that the source depend on the country. For example, in Norway, you have almost all the source of hydro energy, but in Denmark, we have important participation of the coal. Hydro generation is the main source of randomness in this region. And we see that because of the importance of hydro energy, the region is divided in bidding zones. So the zones we see in the map are the bidding zones. These zones can be connected or not. When they are connected, they have can have flow of energy. This flow is always bounded. And for each zone, we have a demand that needs to be attended. And for each hydro in the zone, we have a different water balance equation. So the model for the energy generation problem in Northern Europe has the following features. So first, it's a multi-stage program. Second, we use real and estimated data from the Northern European energy system. We have the time divided in T in days and W in weeks. Uncertainty reveals the first day of each week. So we treat the problem as linear inside each week, and for the first day of each week, we have uncertainty that appears. Inflow scenarios are generated by historical and standard deviation, historical mean and standard deviation, and we use the log normal distribution. So because the log normal distribution is that the better describes the inflows. Demand is the deterministic and varies with time. Wind is considered as deterministic because hydro energy is the main source of randomness in the region. And the decisions variable includes the reservoir and spillage levels for hydro power plants and the generation for both hydro and other power plants. So to deal with the multi-stage setting with our three-stage approach, we put in place a rolling horizon mechanism, here abbreviated as RH. So here we have the formulation for the multi-stage, the mathematical formulation for the multi-stage stochastic problem. And you can understand what it means by this tree. We can separate nodes by weeks. So the first node corresponds to the first week. The following two nodes corresponds to the second week, and so far and so on. And when we are, for example, in week 2 in the first node, we need to take a decision that takes as deterministic the event that happened before in week 1. and that takes as random all the subtree after this node, and take it in account to make the decision. So when we have one first stage decision for each node, we call it an implementable policy that has this characteristic. So about rolling horizon will take, for example, for week 2, it will take as deterministic the event in week 1 in blue in the drawing, and the subtree in square blue is consider the randomness that came after the node. Rolling horizon will divide the problem in a set of 3-stage problems. So first, the first stage problem corresponds to the first week, and the second stage problem corresponds to the all future. After, we will continue to following a random path, and we will continue to divide the problem between a first stage problem and a 3-stage problem that correspond to the whole future. Paths in red and in green represent some samples that we take to represent randomness in this 3-stage problem, in the future cost function. It's different, for example, than SDGP, the stochastic dual dynamic programming. For SDGP, we start showing randomly a forward path. For this forward path, for each node, we take a decision with the approximation of the future cost function we have in the moment, a first stage decision. After, we have the backward path. In the backward path, we do linear cuts that are under approximations of the future cost function. To do these cuts, we use the Lagrange multiplier. Or we can join these cuts to do approximation of the future cost function of the whole tree. After that, we show another forward path, and we compute these first stage decisions for each node. This first stage decision will be possibly better than the first ones we compute, because now we take in account the cuts we have done in the backward path. Like this, we are always approximating better the future cost function. Because when we do the forward path, we have a new point to do the cuts, and we do the backward path, we have a better approximation in this point. So the size of the problem we solve is that we have 30 zones, 29 idle power plants, and 273 power plants in total. Our decision vectors consider the levels in the reservoirs, the generation, the spillage for water hydropower plants, and the flow between zones. If we sum all these dimensions, the decision vector is in R46, and we have 52 stages. There are weeks. Scenarios I, Xi, S are 30 scenarios for the optimization phase and 200 scenarios in the simulation phase. We consider 2 samples, Xi, each one a sample of scenarios, Xi1 to Xi-S. About the choice of beta, as we have already talked about, we have that we can describe the Lagrange multipliers in terms of the water balance equation over beta. We know the possible values for the Lagrange multiplier since we know the cost for other power plants in the system. So we can estimate this value, and you can also estimate how much you can violate the water balance equation, since we can estimate it as a percentage of the total level of the reservoir. With this in mind, we can also estimate a value of beta that we gave something coherent in this context. So, for example, for the optimization phase, we have this reservoir curve that represents the level of the reservoir for the mean level of the reservoir in all zones for SDGP, rolling horizon, and regularized rolling horizon. Here, colors represent weeks. The behavior of this curve is expected since we start in January, so the level of the reservoir is low and is decreasing because there is no rain. And after, in the summer, we fill the reservoir. We also note that in the first weeks of the year, SDGP has a more conservative behavior since the levels of the reservoir are higher. So it's not using this water to generate electricity. This is expected since SDGP visit more nodes in the tree and have a better perception of the risk. Another comparison is between regularized rolling horizon and rolling horizon. We see that the curve for regularized rolling horizon is under the curve for rolling horizon. It's also expected since we can prove that the future cost the regularized future cost function Q beta is under the original future cost function Q. So we expect regularized decisions to be less conservative. So about the overall procedure of the simulation, we have an optimization phase where you use solvers rolling horizon and regularized rolling horizon. We have as output first stage decisions, and you have a simulation phase that use these first stage decisions to simulate more scenarios and different scenarios in the second stage problem. From this simulation phase, we have some indicators of performance, for example, the mean, the variance, and the histogram of price signals. So one observation is that since the Warren balance equation is not anymore a constraint, we need to observe how much this equation is violated. So here we have a graph of this equation, psi x minus cx1 minus wx2x, where colors represent scenarios. This is for the zone NO2 in Norway. So what you see about this behavior is that it is larger here in the 50 week, and we see that this coincides with where the reservoir are more pressed, when we have less water. So this pressure in the reservoir makes us to be more supposed to violate the water balance equation. After we have almost zero, so we expect this constraint. And we have, and it increases a little in the end of the year because of the final constraint that the final level of the reservoir needs to be the same as in the beginning. But in total, we have that the constraint violation is negligible, less than 1.2%. For the whole system, we have the same behavior, and it's more, the total constraint violation is negligible and less than before. 0.01% in max. So about the price signals, so here we choose beta equals 300, which the procedure I have already presented for zone NO2, sorry. So we have that the histogram for rolling horizon have a less smooth distribution than the histogram for regularized rolling horizon in the right. So in blue. So we see that this is similar to what we have found in this simple example that we have seen in the illustration of the approach. We also see that the expected value is a little bit lower in the case of the regularized rolling horizon, and the variance is also smaller. So the variance for rolling horizon is 12.3. And for the regularized rolling horizon is 10.2. When we increase the value of beta, what you see is that this behavior continues. So we have a more and more compact distribution. So with less values, and with a variance that is decreasing. So here for beta equals 1000, the variance is 5.2. But the expected value also starts to move far away from the rolling horizon. So here the expected value is 19.1. So another simulation we have done have the overall procedure, that the optimization phase we use rolling horizon, regularized rolling horizon, and SDGP. As outputs, we have cuts of the future cost function. We use these cuts to each node to simulate a forward path of FDDP, what we call the dual simulation. And from this simulation, we have the indicators of performance. So the mean, the variance, the histogram, and the Wasserstein distance. Since we compare the distance between histograms to know if this distribution is more stable with respect to samples. The behavior we have seen in this simulation can be viewed in these histograms. So, for example, for SDDP, the price is oscillating between 2 or 3 values, and it's closer to a discrete distribution. And for regularized price, we have this more smooth distribution with a similar expected value. So we know that beta reduces the price and variance, but the trade-off regarding constraint violation, solving the original problem, must be found. So in this case, beta equals 300 gives a good compromise. A table that summarizes the results of this simulation shows that for when we run 20 times the overall procedure to compare for different samples how it behaves, we see that the Wasserstein distance of histograms is really smaller in the case of regularized volume horizon, that is 5.64, if compared to SDDP, for example, that is 15.78. Also, we see, as expected, that the mean of the price is also smaller. So for regularized volume horizon, we have 53.23, and for SDDP, 67.95. So the conclusion is that regularization helps us to stabilize the price signal with respect to the distribution of inflows. So about the conclusion and the future works. So the proposal of regularization, regularizing the recost function in the dual provides a mechanism to select the Lagrange multiplier with minimal norm. The regularization applied in a rolling horizon mode for the multi-stage energy problem provides price signals that are more reliable than those obtained with SDDP. And some possible enhancements consider other sources with important uncertainty as wind generation, and explore some possible relations with progressive heading. So thanks for your attention.
Thanks a lot. So I will give the let the first referee, which is in this document, it is Anthony Papa Macêdo. Sorry for the pronunciation.
Thank you very much. Thank you, Clara, for the very nice presentation and the very nice work. I guess I had a couple of big picture questions. So I was wondering, when reading the abstract and listening to your talk today about the applications that you have in mind in general with this work. So is this motivated by, you know, the goal of an energy company to invest somewhere and facing an unclear distribution of prices, or is it more of short-term applications? Could you comment a bit on what was the motivation?
So the motivation is about the comprehension of the distribution of price in long-term problems. So the problem here is that when we solve SDDP, we have this distribution, since it's not just a vector. But when we change the sample, we have another distribution that can be different from the first one. So the question is how reliable, if you can trust in this distribution. So this price are used to make decisions for long-term problems, or for in sense of a year.
I see. So, and when you're talking about getting a different solution from SDDP, that means a different potentially from every run.
Yes, there is not just when we consider a sample. So we have, for example, 20 scenarios. We have a distribution with 20 samples. So this will be a distribution, not a vector. Now we have another 20 scenarios, and we will compute another distribution. So we can compare these two distributions. They should be close, because if you want to trust in this result, these two distributions need to be close. And what we find is that sometimes it's difficult to predict when this distribution will be close, for how much scenarios we need to achieve that. So we use regularization to understand if with regularization we can, with less scenarios, achieve the same stabilization of this distribution.
I think what you're saying. I'm just wondering, without having worked directly with the PSR software, for example, but I would think that in the limit, if you give an iterative method like STDP enough time and allow it to converge to a certain optimality gap, even if it is probabilistic, I would be surprised if the resulting policy is very different. So suppose you allow your cutting plane algorithm to run for a couple of hours, and it comes back with a, given a certain number of forward backward paths, for a certain number of Monte Carlo samples for each forward pass. I'm wondering how much different the policies are. Of course, I agree with you. If you're only drawing 20 samples, it makes sense that you get a very large variation in the policy. But if you allow the thing in a way to stabilize or to run for a sufficiently large number of forward-backward passes with a sufficiently large number of Monte Carlo samples in the forward passes, do you still observe this behavior of policies that are very different?
For what we observe, that even when we have a simple two-stage problem, and we consider, for example, in the first example I gave to motivate, we consider 80 samples. That was really large for the size of the problem we had, and we still have this variation of distributions. So it's distance between distributions and the expected value of the distributions, for example. So sure, we do SDDP since it is in the optimal result, so we don't stop before. But STDP is not in the whole tree. Is not. It's always a representation of the randomness. It's not something that is understand the whole randomness of the problem because of the algorithm how it is.
Okay. Then I have a bunch of basic clarification questions. So if we go to, by the way, just to make sure that I'm not abusing time, how much time do we have for the inquiry?
You have enough time. Don't worry about this. Start.
Okay. Then maybe we can go through the questions that I sent in sequence. So this is kind of the first question I have from the manuscript, and it also relates to slide 18. I was wondering what extra the AX equals B constraint imposes on the problem in slide 18. In slide 18.
We are just looking for the slides here.
Yes, here.
Here, okay. So slide
18.
18. Okay, so you need to. Okay.
So the AX equals B, given how you define B, what extra constraints does it introduce to the problem?
This AX minus B?
Yeah, equals 0.
I'm not sure I understand extra constraints in which the AX minus B is supposed to represent.
Given the way you define B, is it not enough to just require that X is in the capital X set?
Not sure I understand. What we are supposed to represent is this is the one level formulation that is in slide 17. Let me see here. In slide 17, we see what we want to represent. So, for example, for the problem P, the AX minus B is the water balance equation. That is, so X is summarizing X1 and X2 side, and T and the AX minus B is the water balance equation.
Okay, so the X is temporal. It's considering both the stage 1 and stage 2.
Yes, exactly.
And then if we go to slide 18.
Okay.
Okay, so it's the temporal coupling constraints, essentially. All right.
Okay.
I'm not sure if I'm like, it seemed to me that once you, I would think that the X equals B constraint should impose something additional on top of the X belonging to the set capital X, but here, given the way you define the vector B, it seems to me that X being in capital X implies the equalities.
I'm not sure if I understand your question. If I can clarify.
I can intervene. Let me intervene. It's just a way of writing, Anthony. There it's saying you cannot put any B. The B, otherwise the P will not have a solution. You have to say that the inflows have to be enough. They have to be so that with all the capacity plus all the deficit, it can be taken care of. We are only saying that P has a solution there with this definition of B that belongs to the set.
Yeah, not even has a solution, but just says that the problem is feasible. That's all.
Yeah, that doesn't have an empty feasible set.
Okay. All right, then in chapter 3, you present a model in section 3.1.2. I was wondering, I was curious if in the Norwegian case study you were considering also a river network.
No, we are considering just hydro. I think it's chapter 3. So, but I think
Yeah, you have
I can answer without. So no, we are considering just hydropower plants. So we are not considering these different levels that I have already seen works that consider like that. But we are considering isolated hydropower plants, not a river.
I see. Okay. And then regarding the property of getting a solution with the smallest norm, is that something that is practically relevant in your work with ENGIE?
No, it was not applied to the energy generation problem. Since there we are, the Lagrange multiplier is unique. So we don't have this selection of Lagrange multiplier.
So maybe if I refer in particular in the manuscript, if we go to page 23.
Okay. Okay, I'm in page 23.
You mentioned the next consideration is that having as output a solution with the smallest norm is important when dealing with prices. And I was curious about the motivation of that statement.
In fact, the problem is that when you don't have a selection, the answer you receive is arbitrarious. So it's not you don't know in each position of the set you are. So the important thing here is that we define a mechanism that makes you know where you are in the set. And in terms of prices, you have an interpretation as the minimal norm price.
Yeah, and I mean, I understand the value of getting a unique answer, but I was just wondering if the property of a minimum norm price is something that was considered as being practically relevant, or it was just convenient because it was coming out of the theory.
It's surely an extra information. I don't have an application to show to you here. It's relevant because of this and that, but it's surely an information that you know in each position you are, and you know that it's the minimum norm. So yes, that's it.
Okay, that's clear. And then in chapter 4, in page 29.
Okay, chapter 4, page 20. Okay, okay, the first page.
Page 29 of chapter 4 is the third page.
Third? Okay. I think okay.
So you refer to this example, which I think you also had in your slides, and again, I was a bit struggling to understand the motivation in the example. So what I mentioned in my notes here is, why would one manager only sample negative numbers and the other only positive? Then I mentioned, why not apply sample average approximation with a very large number of samples, which is computationally tractable. So I'm wondering if you could, for the sake of my better understanding of the context, comment a bit in more detail about the example.
So about that, we gave surely an extreme example where one is just taking negative values and the other just positive values. But what we want to exemplify is that in one sample, you have more negative than positive or inversible. So in this example, since you understand the problem, I'm sure anyone would do good samples, but in a real context, you don't understand how your samples should be. So the fact is that we are comparing two samples that are taken in different ways, and not exactly one sample that is positive and one sample that is negative. This was just to exemplify the context.
But the actual thing your end game here is not necessarily the mean of the price, it's rather the stability of the distribution. That's what you are rather interested in. It comes back to
here we
question.
Sorry?
It comes a bit back to my original question of what is the underlying application. I mean, I'm wondering if it's in the context of investment problems or investment problems with risk aversion. So I'm trying a bit to understand what is the underlying thing that's considered as being desirable, if it's getting the mean right or getting a stable distribution of prices.
In fact, it's the mean and the stability are in this case joined. So we have a mean that is closer to the mean of the real problem, and also we have stability with respect to distribution. So it's both in this example.
Because, you know, if it's just the mean that one might be concerned about, you could argue that you can land on, you know, again, I mean, the counter argument to all of this would be that we can rely on pretty heavy computational machinery, especially if you do things in parallel. So provided a large enough number of samples, even without the regularization, you are likely to land quite close to the true mean.
Yeah, sure.
So if you're only isolating the mean as the quantity of interest, I'm wondering about the additional value of the approach.
Yes, I understand. The fact is that if you have enough time and you can sample as many samples as you want, I agree with you. The meaning of our approach is to understand the behavior when we do this zero regularization in respect to this stabilization, and how the mean is distant from the real mean of the problem. So we are observing these two aspects, and what we are showing is that we need less samples than when we are working in the original problem.
Then in page 58, you refer to a dual implementable policy.
Sorry,
So
what's the
that's
page?
something that
Which page?
in page 58.
Okay. Okay.
You refer to a dual implementable policy, which is something that maybe it's for lack of my own education on the topic, but it's not something that I think is, I mean, I'm not sure if I've ever encountered it before. So what is the definition of that?
So an implementable policy is a policy that respects, is that what I explained when I showed I have shown the tree. So it's a policy that respects that when you are in a node, everything that came before is taken as deterministic, and everything that comes after is taken as random for you. So your decision for each node depends on the randomness of the problem of the subtree that comes after the node. When we consider the set of these decisions, we call it implementable policy.
And you apply the same concept to the price process.
Exactly. Yes.
Okay. I see. And then regarding the actual case study that you investigated, so just to make sure, first of all, I understand figure 5.7. So the three different trajectories here that we are looking at.
And
in figure 5.7, which is also the figure that you showed in your presentation.
Okay.
The three different trajectories now correspond to
okay, so the three different trajectories correspond to different algorithms. So we have SDP, we have rolling horizon, and we have regularized rolling horizon.
And then why do we have these? Right. Okay. So it's right. Okay. Good. And then, so your procedure, basically, just to make sure I understand in practice what you are proposing is, you would run the regularized rolling horizon approach with the goal of getting a more stable price output, which possibly would also navigate you a bit differently in the primal space, which I guess is okay. But how would you decide? I guess you hinted at that during your presentation, but you present asymptotic results in chapter 3 or 4, I think it is, of your thesis. But what exactly would you propose here as a procedure? Exactly, would you propose an iterative tuning of the beta, or using that formula that you presented in the slides to tune the beta once and for all? So I'm a bit trying to understand in practice how I could use the theoretical firepower that you developed.
Okay, so I think we can understand things separately, maybe. So we have some results that are about the importance of the regularization with respect to defining a mechanism to select a Lagrange multiplier when we have a not unique Lagrange multiplier. And we have another set of results that are in the direction of the stabilization of the distribution, and how far we are from the mean of the real problem. So that there's two different directions, in fact. So about, for example, this distribution, how the behavior of the distribution, you can see, for example, in this example I present, we can actually show mathematically that the variance decreases, and we can see what happens. When we are in this more complicated case, as the energy generation problem, we can see it in practice. So that's the idea.
Yeah, but are you proposing some sort of an iterative implementation of the regularized rolling horizon? And if not, how do you decide on which regularization value to use?
In the
For the
direction,
second, for the time series with the circles, for example, how do you tune the beta?
the time series, sorry, with?
So the policy based on regularized rolling horizon.
When you were talking about how to choose the parameter beta, in this case?
Yeah.
Okay.
Yeah.
So what we propose is in our real or with real and estimated data, we know the value of beta because of the real problem. So we estimate because we know that we cannot violate the water balance equation more than a percentage of the total of the reservoir, because it has a physical meaning. So what we find also in the example is that we can understand the value of beta also in the perspective of understanding how much we want this to relax this equation.
Okay. Okay, I see. And then just to make sure I understand the example correctly, the SDDP policy that you simulated in itself doesn't violate the primal constraint. No. It's rather okay.
No.
And then that much is clear. And I think I had one more question about the example. Right? Yeah, you mentioned in the slides, if you could go back to the slide.
Okay.
I was a bit curious about the state variable count. So you...
In which slide, please?
I don't remember. Let me find my notes here. So slide 46, I think.
Okay, so 46, okay.
So it's 406 dimensions coming. The plants are having state variables due to ramp constraints, or?
No, the all randomness in this problem came from the water balance equation. So it came from inflow.
Right, but why do you have 406 states?
Sorry, I didn't understand.
So you in the second bullet, you mentioned that your state vector is in R of 400, R to the 400.
Uh-huh.
That is the result. That is the result of 29 plus 29 plus 273 plus 75.
Okay.
So where is that coming from, if you can explain?
Okay. It's just because, for example, when we consider the level of the reservoirs, so it's one level for each hydropower plant, so 29.
Yeah.
When you consider the spillage, it's also 29. When you consider the generation, it's 273 because it's one for power plant. And we have 75 zones because the flows are not between power plants, are between zones. So it's a different number.
Right. Okay. So you're counting real variables that are in a given stage, as opposed to the ones that couple one time period to the next. But in reality, the only ones that really couple are the water levels, right? You're not considering sort of autoregressive.
Yes, you can separate it as a state variable, and the variable that are really in the random problem are the variables for spillage and for generation of hydropower plants. In fact, there are other variables that we consider more in the sense of gap, etc. But it's not so important to the model, so I didn't.
But it seems to me that assuming that you were working with independent water inflows at every stage, you would really get a pretty large variation in prices, whereas in a more realistic model with, for example, some autoregressive behavior, you could expect possibly lower variance in price. I mean, a bit more of a stable behavior, possibly. For example, coming from SDDP. So did you try to introduce some autoregressive behavior in your water inflows to see how sensitive your conclusions were?
No, I didn't study the autoregressive behavior, but no, it's surely interesting, but I didn't do it.
But okay, at least I understand the notation better there. And then let me see if I have any questions. There's a bunch of other detailed questions I could maybe interject later during the discussion if we have any extra time left, but this was already really helpful for me to better understand the context of the work. So thank you very much, Clara.
Okay, thank you.
Thanks a lot. So I will ask to Jérôme Malick from Grenoble, which is the second referee of the thesis.
Yeah.
Excuse me, Jean-Marc. Do we have any time limit?
No.
Not really, but let's say
It's a soft constraint.
it's open time.
Well, then I have some. Perhaps I will have some problems. I would like. Could we assume that we will finish at 2 p.m. Rio de Janeiro, which would be like 7 p.m. there?
I would agree, but it really depends on the question. So I guess that the two referees have much more questions than the other members because the advisor already discussed a lot with Clara.
Okay.
And so it would be,
Okay. I would just ask to try to, let's say, limit ourselves a little bit.
okay.
Thank you.
Please, Jérôme.
Okay, so I still would like to take 1 minute to thank you, Clara, for this very nice presentation and more generally for your work. So I wanted to point out that what I like in your work is that you put together very different aspects, some theoretical you got some theoretical results. You applied also some nice theory, variational analysis, for example. I like also the illustrations that you gave on some toy problems because I think they really illustrate very well the point that you wanted to make. And of course also the application on real life problems. So it's for me it's a nice applied math work. So congratulations for this. And also I like reading your manuscript because it's extremely well written, well illustrated, as I said, and well structured. So I can tell because I'm fighting with my student who is now finishing his PhD. So I can compare your manuscript with his, and yeah, he has some work to do. I also wanted to mention a point actually that I like very much in your work is that it somehow show that optimization is important, because usually when you discuss with practitioners or people close to applications, they say, okay, I modelize my problem, I make this assumption, this model, and after some work, I have an optimization problem, and then I solve it, and that's done. And actually, your work is show the other way, is that if you have a problem after modelization, then if you solve it with different algorithm or with an algorithm with different implementation, or if you run it on different machines, then you can get possibly different solution. In your case is price indicators, and so optimization really matters here, and it's also a point that is of current research in machine learning community. So the implicit bias of optimization. So that's what I wanted to say, and so I think I can limit myself to maybe two type of questions. The first is about, the first is the most important one. It's about some perspective on your approach. So you use the L2 norm to regularize your dual variable. I understand that you want to have a strongly convex norm to have a uniqueness, but you could, I don't know, we could imagine using another type of norms, and for example, adding also some sparsity in the solution, for example. And I guess that much of your theory can extend to this case, or maybe I'm wrong. Could you comment on this?
Yes, about the choice of L2. In fact, it was motivated by because we want the future cost function to be more regular. So when we have, there is a result in the manuscript that talks about the how this kind of regularization in L2, how it makes the future cost function more regular, because we expected that this behavior of the future cost function will influence what we see in prices. So that's why we choose L2 in this case. In the beginning, we have also thought about L1 or any other norm, but that's why we choose, because it's also because it's simple, but because we can have better results. We can have a future cost function that is differentiable, that we don't have one-time differentiable, that we don't have in the case where we don't regularize. And we can also see that it is convex by parts. So it's an interesting characteristic for us. And about sparsity, I think it could be done with a case where sparsity is necessary. In this case, since the price, we are not dealing with a number of variables that is so big, I don't know if sparsity is something important in the problem, but I think it could be used in a problem where it is.
Okay. So if we focus on the L2 norm, so I knew this paper that I mentioned by Wellington and another colleague from Brazil, I think, who present a proximal bundle method, a variant of it, which has this property of convergence toward a minimum norm solution. So is there a link between this algorithm and your regularization?
I don't know. I haven't read the article. So that's one of the articles, because I've read two articles that you list, but I don't remember this one. About I don't know.
Okay, so it's just, I think it's it's a natural question, because they have suppose you use a bundle method in your case, you will get a solution, and if you use this version of bundle method, it is supposed to get to minimal norm solution as well, the same as yours. So
very interesting.
I guess it is something you should look at.
Yes. Sure.
And so the main question here about your approach, again, that I like because it's simple but powerful. We saw the results. I like it, but what would be what would give something more sophisticated, for example, an augmented Lagrangian approach, or more than just a regularization?
Yes. Yes, I understand your point.
So have you thought a little bit on this? And I guess that the complexity of putting this approach in practice is the most it's an obvious drawback compared to the simplicity of your approach.
Yes. Yeah, I haven't thought about it.
Okay.
But yes, I understand your.
Okay. Maybe I can just add a quick question because it's also for myself, for my culture, because I worked a little bit on progressive edging, and I saw during your, I think it's on your slide on perspectives.
Yes.
Mention it quickly. Is it relevant to compare this approach with the one that you already compared? So yours, SDDP, and the vanilla rolling horizon.
Yes. In fact, I think it's a very interesting idea. I didn't thought about it. I didn't think about it. I thought about it because of your comment.
Mm-hmm.
And in fact, I know a little bit about progressive hedging, but more in the finance applications and this kind of the discussion. So it was not something that I was comparing. But it's true that it's an interesting point to be compared with my approach.
Okay, so I don't think it's gonna change completely the picture. So anyway, so the most important comparison indeed is comparison with the basic rolling horizon. Mm-hmm. But it was just for my culture, and because I guess that if you write the equations and the algorithms for progressive edging, you get some box-like term that looks similar to what you have also. That's why it's a natural question as well. Okay, so I won't take too much more time. Thank you again for this nice presentation. Congratulations for your work, and I'm done.
Okay, so let us continue with Alfredo, Noel, Iusem.
Alfredo.
Okay, I'm coming in. Yes, I'm here. Do you hear me?
Yes.
Okay. So, well, first, let me tell that I want to emphasize that Clara's thesis is a very, very good piece of work, very well written, much better. The English is almost impeccable, and it's very well presented, very clear, and I think it's a quite interesting contribution because we have some theoretical progress, basically what was published in the Jota paper, but also I found it very interesting, the applications. So congratulations, Clara. I guess that's at the level of the best theses which have been defended within the optimization group at IMPA. And so after, let me ask you just a fast question.
Okay.
You consider the possibility of, I mean, I'm sure that you have considered it, but let's say, how much harder if you go over the linearity, let's say, and assume that the objective function is nonlinear? How much is changed? So you have, for instance, a convex objective rather than linear. Do you think that you can extend your results more or less easily?
So that's what in the first part, where we consider this abstract quadratic program, we consider the nonlinear case. So we consider exactly what you were talking about, and we can generalize with some conditions that we discussed in the work. So we have some conditions that are involving this nonlinear part. Sometimes we need H to be positive semi-definite. Sometimes we need that it to be positive semi-definite in some set.
Yeah. And if you consider a case, let's say convex but not necessarily quadratic.
Okay, but that's.
I mean, going.
In our work, H can be anything at the beginning. What we see is that in conditions it appears this restrictive points. But when we
but
start,
I understand that H is a matrix or not.
Yes. Okay, so you want it. Okay, you don't want this. You need to
H
propose.
Matrix.
Okay. So this I haven't thought about how it could be.
Yeah, what I was saying is that suppose that you have convex objective linear construction.
Sorry, the audio.
Okay, sorry, I'm not listening to you now.
Is cutting.
Well, let me put it this way, Clara. Not to answer me that, but I think that an interesting thing would be to go over that part again, just assuming convexity of the objective and putting the quadratic regularization in the dual.
Okay.
Well, but just with, I mean, linear constraints, convex objective, and that I mean, the future as a project for future, not necessarily now. So, in any case, once again, I'm very happy with the outcome of your work, and that's all for the time being. Thank you very much, Clara. Also, the exposition. This is what the oral presentation. Congratulations.
Thank you. So let us continue with Guillaume Erbs from the society ENGIE. Guillaume?
Yes, I just unmuted the micro. I would like to thank Clara. I thought that the presentation was very clear. I would like to thank her for all the work she did while she was being with us. I wanted to mention that I liked reading the thesis as it was outlined by other members of the jury. I think the structure of the thesis and the writing made it very easy to read. I think I also like the fact that there are very theoretical parts and also quite a lot of numerical applications, which is I think well balanced. I would like to make a very quick comment on the importance of having stable prices. This kind of models are used for two types of decisions. In the short to medium term, the results of these types of models can be used to forecast prices for trading. So if doing two runs of the model gives you two distributions of prices, then there is an issue to take your positions. And there's also the application in the longer term on investments, and it's also the same. If you want to make an invest in an asset, you need to have a forecast of prices that you can rely on. And this is very so this is very important for people in the energy companies. I would like to congratulate Clara also for her evolution in these last 3 years. She has passed successfully quite a lot of hurdles. The first one was to move to France and learn French, which maybe in the beginning being surrounded by people speaking French was difficult. Then she also passed the hurdles of learning GAMS to model a realistic numerical application, and also, which was maybe even more difficult, to deal with a huge data set. Because, well, actually the slide that is projected somehow shows the amount of data to be dealt with is huge, and Clara was not really used to deal with such data. So I think it was very successful for her. Well, these last 3 years were very successful for her. I will not ask questions because I think I have asked many questions to Clara in the last 3 years. So it will be enough. You can pass to the member of the jury.
Thanks a lot. So let us continue with Claudia Sagastizábal.
Okay, thank you. So, well, I have also asked many questions, and my colleagues, well, what I want to say is I want to thank the reviewers, and I want to say, and ENGIE and Clara, but I want to point out that this is a successful enterprise because there was trust involved in among all the partners. There was trust in Clara that she was going to the unknown in doing this project in industrial mathematics that no one knows much what it is about. Before having done, now you know better what is industrial mathematics. So going from the theory until the real data. There was trust from Jean-Marc to accept being part of this project, then to go back to my beloved Paris one of origin. Trust from ENGIE that we would succeed, and trust from IMPA. So it is really an enterprise where everybody was willing to go into some uncertainty that got stabilized with this quadratic term and this parameter beta, and I'm happy that we are reaching a successful ending. So, well, that's more or less all I have to say. So thank you Paris One, thank you ENGIE, and thank you Anthony and Jérôme for your reports. Okay, that's all.
Thank you.
Okay, thank you. So I will ask to Jean-Marc Bonnisseau to continue.
So it was a great pleasure when Mikhail and especially Claudia came to me several years ago to propose this thesis with Clara, because actually I work on the electricity market from more an economic point of view since many years, and it was really interesting for me to go back to this issue and to contribute. And I was particularly pleased because in the French community, this is important to have mathematics motivated by applications. And here we are really in a true subject at the interface of the theory with real numerical experiments and real data and the real interest of a big company like ENGIE on the topic. So that's the kind of PhD topics that I like, because we are really mixing a lot of things, and we are really contributing for international relationships between IMPA and Paris, and for the cooperation between academia, and the private sector. So really, thank you, and I'm very pleased to have worked with Clara, and I would like also to thank the two referees for their work, and the job at the end is very, very interesting. I expect that, in my mind, it's not a definitive work. So a lot of line of research are open now, and I will not ask real question, but just two suggestions. The first one, from let's say more an economic point of view, is to have an interpretation of the selection of the price with the minimal norm in terms of the behavior of the firm and aversion of risk. In my mind, so a little bit Guillaume speak about that, because if we have too many distribution, we don't know how to deal on the market, or which assets. So in terms, but it's really a work about the decision theory and behavior under uncertainty, to justify these prices, these particular prices among others, as the one for which we minimize some kind of nonlinear objective function. Okay, first point. I guess that you have nothing to say about that, but it's first. The second point is that in your picture around the yearly problem, you know that you have some period where you are in trouble. The end of winter, and at the end, due to the fact that you want this strange let's say, final condition about the level of the reservoir. But let's say, for the final, this is an artifact of the model. But what it would be interesting in my mind is not to have a uniform beta, and to maybe to decompose your constraint and to focus on the key constraint, especially for the shortage of water in the reservoir during this period, and maybe to have a more so not the same level of
toleration.
Yes, of calibration for this beta, and to see, we don't know exactly where are the problem, but we have with the experience and where are the difficulties. And I guess that in many problems, this is the same thing. We know that at some period we are very far from the boundaries of no problem, but and to focus and maybe to have this let's say mixed, where beta is a little bit adapted, not period per period, but for some big time. So and probably it would be help not to have this shortage of water could be very, very problematic, as we can see on the price of the electricity in the market. But for example, we had a very strange prices during the spring time in Europe on the electricity market due to wind, actually, because a lot of wind in Germany, a lot of renewable energy, and so it could be interesting. So I will not continue, but to be short, but it seems that maybe there is a point of research there from an economic point of view, as well as from, let's say, numerical optimization, numerical problem. So thank you to all of you, and especially to Mikhail and Claudia for this cooperation, and thank you for you, Clara, to have produced so good work. And your presentation was really. I read your slides before, and I guess that your comment was really very good on top of your slides. Thank you.
Thanks a lot, Jean-Marc. So let us continue with Mikhail Solodov.
Well, thank you. Of course, I also will not be asking any questions at this stage. So just want yet again emphasize this three-way collaboration, which of course was an opportunity, but potential could also lead to some complications. But so congratulations to everybody for navigating this well and bringing things to these successful conclusions. Well, that's all. And thanks, of course, with Teresa and everybody else who participated in the defense. So that will be all. Thank you.
Thank you.
Thank you. So I will have a short questions, comments. So first, I want to join my colleagues and congratulate Clara for the quality of both her manuscript and presentation. And so a small question. You emphasize the fact that the penalty parameter sequence beta k is not necessarily monotone. Is there a numerical interest for considering such a case?
No, it's just the terms that you have seen as more standard in the always emphasize this. But in fact, if you have a subsequence that is monotone, you're getting the same result. So it's because, in fact, what it proved is that it's bounded independent. When we need it to converge to a really original solution, you need it to converge to zero. So in some sense, we need it to be decreasing, or at least a subsequence.
A subsequence, yes. I agree. Yeah. Second comments. In your future plan, you may imagine to introduce a stochastic component for the wind. I imagine that it will increase the difficulty for computation, but it will increase the quality of economical results. So, but will there be will it introduce new mathematical difficulties?
Yeah, I think because the randomness from scenarios and inflows, I think they are easier to model since it is just. In fact, I don't know how to treat data for the wind case, because wind is not just something that you take in a box. So I think the data treatment would be more important in the sense of how do I model these scenarios, how do I propose the scenarios, etc. And also, I think the wind has more important variations in years than because inflows has with seasons. It's really the variations are clear, like temperature. But wind, I don't know how it could behave in this way.
So my last word will be in fact more a comment than a question. So in France, France has promised 10 years ago to evolve about the management of hydropower plant. In the past, most of the units were managed by EDF, the historical public producer, and in fact, there will be new manager to be chosen by a system of concession. So, and it will represent, as far as I remember, half of the units within the next 5 years. So it's very important for the French case. And a lot of people are reluctant to, for this operation, in the sense that, and among the arguments used by them, there is the idea that in France, an hydro producer, an hydropower plant means in fact a joint production, not only a production of electricity, but also it is a water supply for agriculture, and it's an input for water resource activities, and so it's difficult to modelize those constraints in order to write the contract before the bid process. Is it the case in the north of Europe?
I didn't study how it was put in place in Northern Europe, so I don't have the answer, in fact, of how these constraints are taken in account about. But I think in France, like now it's just a personal comment, not a specialist. But I think in Norway, I have been in Norway when I do a congress there. I did a congress there, and I think they are much more space and and a less population. So I think these constraints should be less important than here in France. There is very considered, but it's just a personal.
Thanks a lot. As I told you, it was more a comment than a real question.
Yes, but it was interesting.
Let us.
So we will switch off the connection and start again in a minute. We just move with Pascal, and we leave Clara waiting for the decision of the jury. Okay. We are back in a second using another connection. Everybody is hearing Pascal?
Yes, I think.
Yeah.
Stand up. So here, it is a pleasure to write the report that we have written together. So Clara Lage made a very clear presentation of her thesis and highlighted her main results. It was quite well balanced between theory and application, and in addition to academic illustration, it treated the case from ENGIE with real data. Her responses to the numerous questions of the jury showed her solid knowledge of the domain. The manuscript contains interesting contributions in stochastic programming, such as stabilization of dual variables in the presence of uncertainty in a context where both primal and dual variables are relevant. This is the case in the energy sector for trading decision in the short terms it is the case in the energy sectors for trading, where both decision in the short term and decision in the long term with dual variables acting as price indicators. The thesis studies the stability of price signals with respect to different scenarios. She combined computational optimization and variational analysis techniques to provide a simple yet powerful solution to the difficulties arising from the non-uniqueness of Lagrange multipliers. The jury has no doubt, that, like the first part, already published in Journal of Optimization Theory and Application, the second one, devoted to the industrial problem, deserves a publication in an international journal of the field. The jury unanimously decides to award Clara Lage the PhD in Applied Mathematics from Instituto Nacional de Matemática Pura e Aplicada and from l'Université Paris Panthéon-Sorbonne, and wish her a successful scientific career.
Thank you.
So, congratulations.
Congratulations. Thank you.
I take also a picture of the screen to have you.
Okay, wait a second.
Okay, so,
Congratulations.
okay, so I have a picture of the screen.
So,
And I will use the picture of Clara.
So,
it's your turn.
It's your turn.
Yes,
it is. It is.
No, I just need to thank you, everybody, for this this work. I work with Claudia and Mikhail from IMPA. That was a long work, a long journey. I'm sure I learned a lot this process. Also with Guillaume for the work in ENGIE. It was also a long time here in France. Jean-Marc and Pascal for the participation here. Jean-Malick, Anthony. So thank you. And I don't know what to say.
You cannot invite us for the po.
Yes, I cannot invite her.
I prepare something, but unfortunately we will drink later.
Santé. Okay. So I guess we finish here.
Yes, thank you to all of us,
Okay.
and thank you for the IMPA administration for the organization of the defense. It was very good.
Obrigada, Anderson, Andrea e Drew.
Nada. Parabéns, Clara.
Thank you.
E aguardo a documentação.
Ciao.
Allez, au revoir à tous.
I don't know how we.
Comment faire pour ça?